Welcome to AP Biology. This video is on water. Water has many qualities that make it essential for life. The properties that make water essential for life are due to its structure. Water is a polar molecule. It's polar because of oxygen's electronegativity. Electronegativity means that oxygen has a strong pull of electrons. So it takes the electrons from hydrogen and it pulls them in close to oxygen. This is going to give the oxygen a partially negative charge and the hydrogens a partially positive charge. So you can see that these bonds within the water molecule are polar covalent bonds. The partially positive hydrogen of one water molecule is then going to be attracted to the partially negative oxygen of another water molecule. They are attracted to each other just like opposite sides of a magnet. This bond that forms in between water molecules are called hydrogen bonds. We learned that a hydrogen bond is a weak bond, but each water molecule, as you can see in this picture, is hydrogen bonded to 4 other water molecules. So even though each individual bond is weak, collectively it makes a very strong force. I kind of think of it like all the water molecules are glued together using these hydrogen bonds. Hydrogen bonds are what lead to all the special properties of water that make it essential for life. The hydrogen bonds are formed due to water's polarity, and water's polarity is due to oxygen's electronegativity. Water has 4 properties that contribute to Earth's suitability for life. Here we see those 4 properties. 1 is its cohesive behavior. 2 is its ability to moderate temperature change. 3 is expansion upon freezing. And 4 is its versatility as a solvent. Number 1, cohesive behavior. Cohesion is water sticking to water. Like we said earlier, all water molecules are glued to each other. This is going to lead to surface tension. Surface tension is kind of like an invisible film on the surface of water. It's really hard to break the surface of water because all those water molecules are held together by those hydrogen bonds. You can see that some organisms like this water strider and this spider here, they are able to walk on the top of water because they don't break water surface tension. Cohesion also leads to capillary action. Capillary action is actually due to cohesion and adhesion. Cohesion is water molecules sticking to water molecules. Adhesion is water sticking to other things. For example, water can stick to the sides of glass. Water also sticks to the sides of tubes running up trees called xylem. Capillary action is caused when water evaporates off of the surface of an object. Since all those water molecules are stuck to each other, and since all the water molecules are stuck to the surface of the object, as water evaporates off of the top of the object, all the rest of the water is going to be pulled upward as a result. This leads to transpirational pull within plants. This is the major method by which water travels from the roots of a plant all the way up to the shoots and the leaves that need it for the process of photosynthesis. Like I said, plants have tubes running up the stem called xylem. Here you see all these xylem. Water is going to enter the plant through the roots. Water is going to evaporate off of the top of a plant. We call the evaporation of water from the top of a plant transpiration. Water is going to travel up these tubes called the xylem. And you can see that within the xylem, all the water molecules are stuck to each other, and all the water molecules are stuck to the sides of the xylem. So when water evaporates or transpires off of the top of the plant, that's going to suck all the rest of the water up through the xylem. We call this transpirational pull, and it's absolutely essential for plants. Water is able to defy gravity and get to the leaves that need it for the process of photosynthesis. Water also has the ability to resist temperature change, and in my opinion, this is the most important property that gives rise or allows life to exist on Earth. 3/4 of this planet are made up of water, is made up of water. Water has a high specific heat. Specific heat is defined as the amount of energy needed to change 1 gram or 1 milliliter of water by 1 degrees Celsius. The specific heat of water is 1 calorie per gram or 4.168 joules per gram or milliliter. That's very high. So it's very difficult to get the temperature of water to change. 3/4 of this planet is made up of water. Most life is contained within aquatic ecosystems. These aquatic ecosystems are extremely stable. They don't go through large temperature changes because water resists temperature change due to its high specific heat. 3/4 of most organisms' bodies are made up of water. This is also really important. This keeps the internal temperature of an organism, like ourselves, constant as well. When temperature change increases or decreases dramatically, it could be extremely harmful. Since 3/4 of our body is made up of water, this does not take place. Due to water's high specific heat, it also has a high heat of vaporization, meaning it takes a lot of energy to get water to evaporate. This is important to organisms, terrestrial organisms that live up on land, because it causes evaporative cooling. When water evaporates off of the surface of an organism, it leaves the surface and the organism cooler as an end result. Temperature is a measure of kinetic energy. It's a measure of how fast the water molecules are moving. The faster the water molecules are moving, the higher the temperature of water. The fastest moving water molecules are going to be the first ones to evaporate. Therefore, all the water molecules that are left on the organism are moving much slower, and as a result have a lower temperature, cooling that organism off. This takes place when we sweat. It takes place when a dog pants. These are all methods of evaporative cooling. We said that temperature is a measure of kinetic energy. So as water cools down, water molecules slow down. This causes them to pack closer and closer together. So colder water is more dense. However, when water converts from a liquid to a solid, these rigid hydrogen bonds form, and they hold the water molecules in a position that actually makes them further away from each other. So as water cools, it becomes more and more dense, but when it freezes, it actually becomes less dense. This is important because it causes ice to form on the surface of the water, on the surface of the lake or the surface of the ocean. This is extremely important because it's going to insulate all the water below it. It's going to create a more stable environment for all these aquatic organisms that live underneath the ice. If this didn't happen and the water froze from the bottom up, it would kill all the organisms that live in that aquatic environment. Water is also an extremely versatile solvent. Hydrophilic molecules are able to dissolve in water. Hydro meaning water, philic meaning loving. Hydrophilic molecules are polar. I always use the phrase like dissolves in like. Since water is polar, other polar molecules are able to dissolve in it. They are hydrophilic. Some good examples are things like salt and sugar. Hydrophobic molecules do not dissolve in water. They clump out. Hydro meaning water, phobic meaning afraid of. Non-polar molecules separate out of water. A good example of a hydrophobic molecule is going to be a fat or a fatty acid. They're made up of carbon and hydrogen, both not electronegative atoms, cause no distribution of charge, and as a result do not dissolve in water. When we dissolve a solute in water, the solute could be something like sugar, could be something like salt. Water would be the solvent and it forms a solution. We can measure the concentration of solute in the solution using something called molarity. Molarity is defined as the number of moles of solute per liter of solution, and it's just basically a unit of concentration. To figure out the molarity of a solution, or to create a solution of a particular molarity, we first determine the molecular mass of the molecule. So if you're making a solution of glucose, glucose is C6H12O6, we first figure out the molecular mass of glucose. Once you figure out the molecular mass of glucose, you take the molecular mass and you measure out the molecular mass in grams. So whatever the molecular weight or mass of that object is, you measure out that number in grams. You put that amount of grams in 1 liter of water, and you have just made a 1 molar solution. If you look at all this middle stuff here, it's actually more complicated than I've described it, but I'm giving you a simple way to make a 1 molar solution. You take the molecular mass, you measure out that amount in grams, and you put it in 1 liter of water. 1 molar solution. You can then adjust that to make solutions of different molarities, like a 0.5 molar solution or a 2 molar solution if you want to. Here you see what happens when you place a hydrophilic molecule in water. Here we see salt, NaCl, and you can see that the NaCl dissociates, breaks down into sodium and chloride ions, and they are found in between the water molecules, which is why it dissolves. Salt is going to be polar, which is why it's hydrophilic. Water has the ability to ionize, to form cations and anions. Water spontaneously dissociates into hydronium and hydroxide. Hydronium being H3O plus and hydroxide being OH negative. Acids and bases either increase the proportion of hydronium or they increase the proportion of hydroxide. An acid is defined as a substance that increases the amount of hydrogen ions or protons in solution. So an acid is a substance that donates protons or hydrogen ions to the solution and therefore increase the proportion of hydronium. A base is any substance that increases the proportion of hydroxide in solution. Bases can do that 2 different ways. Number one, they could donate hydroxide right to the solution, or they could also take in hydrogen ions. By taking in the hydrogen ions, again, you're doing the same thing. You're increasing the proportion of hydroxide in the solution. You have strong acids and bases, and you have weak acids and bases. Strong acids and bases completely dissociate. You do not have a reversible direction. You do not have a reversible reaction. The reaction goes in one direction. A strong acid is hydrochloric acid, HCl. When you put HCl into water, it completely dissociates, completely breaks down into hydrogen ions and chloride ions. You're donating hydrogen ions to the solution. You're increasing the proportion of hydronium, so it's an acid. Sodium hydroxide is a strong base. It completely dissociates into sodium and hydroxide, increasing the proportion of hydroxide in solution. Therefore, it's a base. Weak acids and weak bases do not completely dissociate, meaning that reaction is reversible. It's constantly going back and forth. Here you see a weak acid that has a reversible reaction. I think this is carbonic acid. And here you see a weak base. And again, what makes them weak is that the reaction is reversible. It's going in both directions. You can see here that ammonia is a base, ammonia is right here, not because it's donating hydroxide, but instead because it's accepting hydrogen ions, increasing the proportion of hydroxide in the solution. A major problem that we're dealing with today in the oceans is called ocean acidification. Our oceans are progressively becoming more acidic. That is due to the increased amount of carbon dioxide in the atmosphere. Carbon dioxide is being released as a result of fossil fuel burning and other things that are occurring in today. Carbon dioxide reacts with water and it forms an acid called carbonic acid. So you can see that these oceans are becoming more acidic. Well, what's a carbonic acid actually doing? It reacts with another molecule called carbonate to make bicarbonate. Okay, well, why is that a big deal? Well, carbonate is really important to reef-building organisms like coral. Coral use carbonate to make calcium carbonate, the substance that their shells are made up of. However, carbonate's not available because carbonate is reacting with the hydrogen ions being released by carbonic acid, and it's forming bicarbonate. So that carbonate is not available anymore to the corals to build their shells. As a result, we have destruction of many coral reefs occurring in the atmosphere today. And here you see some different pictures of a particular coral reef over time. And you can see that this coral reef is being destroyed because of ocean acidification. Carbon dioxide reacts with water to form carbonic acid. Carbonic acid donates hydrogen ions to the solution, to the water. Those hydrogen ions react with carbonate to make bicarbonate, and therefore the carbonate is no longer available to the coral in order to make their shells. Very destructive process. We can solve this by reducing the amount of carbon dioxide in the atmosphere. Burning of fossil fuels also releases sulfur oxides and nitrogen oxides. They work a lot like carbon dioxide. They react with water in the air, and it causes acid rain or acid precipitation. When acid rain falls, it's going to damage life in lakes, in streams, and it changes soil chemistry, right? It's making everything more acidic. And most ecosystems work at very specific pHs. What is pH? pH is a measure of the amount of hydrogen ions in a solution. Pure water has a pH of 7. 7 is neutral. To be neutral means that you have equal amounts of hydrogen ions and hydroxide ions. In other words, you just have pure water. A pH of 7 right, what you're actually looking at is the molarity of hydrogen ions in a solution. A pH of 7 has 0.00000001 moles of hydrogen ions per liter. Written in scientific notation, this is 10 to the negative 7. What we do is we take this exponent here, the negative 7, and that becomes the pH, a pH of 7. So if you have a pH of 7, you're going to have 10 to the negative 7 moles of hydrogen ions, and you're also going to have 10 to the negative 7 moles of hydroxide ions, because they're equal in a neutral substance. So if you take the amount of hydrogen ions and you add the amount of hydroxide ions, together they always add up to 10 to the negative 14. Here you see the pH scale. You see pH of 7 is neutral. You have pure water, you have human blood, both relatively neutral, and you have equal amounts of hydrogen ions and hydroxide ions. Again, they add up to 10 to the negative 14. As the pH goes down, as you go from 7 down to 0, lower the pH means that the substance is more acidic. 10 to the negative 2 is a much larger number than 10 to the negative 7. So the lower the pH, the more hydrogen ions there is. If you look at something that has a pH of 2, like gastric juices, they have 10 to the negative 2 moles of hydrogen ions. They have 10 to the negative 12 moles of hydroxide ions. 10 to the negative 2 is a much larger number than 10 to the negative 12. As you go from a pH of 7 down to a pH of 14, or I should say up to a pH of 14, the substance has less and less hydrogen ions and more hydroxide ions, and therefore becomes a stronger and stronger base. If something like oven cleaner has a pH of 13, that means that there's 10 to the negative 13 hydrogen ions, which is really small, and there's 10 to the negative 1 hydroxide, which is a very, very large number. Again, the pH is always referring to the amount of hydrogen ions. Buffers are going to be substances added to a solution, added usually to a chemical reaction, that prevent change in pH. They're usually combinations of hydrogen donors and hydrogen acceptors. So if a solution is becoming more acidic, the buffer will accept hydrogen ions and return it back to the way it was. If a substance is becoming more basic, then the buffer will donate hydrogen ions to keep it where it is. It's important to understand that buffers, they do not make a solution neutral, but they keep the solution at the pH of where it belongs, the original pH. That completes this. So, no, you're good. I stopped. I finished. I love it. I have like this whole list. I want to get them all done, but